Hello and welcome back to the second part of Families of Polynomial Functions lesson. In this part, we will focus on finding the equation of a polynomial function when certain features are given. Recall again that a family of polynomial functions is made of a set of polynomial functions whose equations have the same degree and whose graphs have same or common characteristics such as same number of x-intercepts and same values of x-intercepts. In a family of polynomial functions, the equations may have different leading coefficient. So what does a family of polynomial functions look like algebraically and graphically? So here I brought as an example the equation of a polynomial function m of x equals 2x minus 3, x minus 4, x plus 15, and kx negative 15, x minus 3, x minus 4, x plus 15. So as you can see in here, we have two equations in factored form, and if you look at it closely, you notice that the factors in each equation are the same. So we have x minus 3, x minus 4, and x plus 15, which means that the roots of this equation or the x-intercepts will be the same. So I will start off by graphing the first one. It's not going to be a precise graph, a sketch, I would say. So the x-intercept is at 3, 4, and negative 15 here. And the x-intercepts will be 3, 4, and negative 15 here as well. So here we go. I'm going to mark the x-intercepts first using the respective colors. Let's say 3, this is 4, and this is a negative 15. Okay, so the scaling is a little bit off in here, but we are just trying to sketch the graphs to get an idea what they look like and what connection they have. And the same thing will be for the function kx. Now, if you look at the leading coefficient for mx, we have a leading coefficient of 2, which is a positive number. It's a cubic polynomial function, which means that it will start in quadrant 3 and end in quadrant 1. So if you were to draw this graph, this is what we would see. Now, for the second function, kx, we have a leading coefficient that is negative in a third degree polynomial function, which means that the graph will start in quadrant 2 and end in quadrant 4. So it will be a bit steeper, or a lot steeper, I should say, because leading coefficient is quite large compared to 2, but this is the idea of two functions that belong to the same family. So what they do have in common is only the x-intercepts. The behaviors may be different or may follow different patterns. So in order for us to be able to identify the shapes and the equations in a family of polynomial functions, we need to go over a few features. First of all, recall that the order of roots always will determine the shape of the graph at the x-intercepts. Okay, then it is a very important feature to mention since we will be graphing equations of polynomial functions from the same family. So in a first order root, we will see the graph intersect the x-axis and go from positive to negative y values and vice versa. So it will be a clear, let's say, x-intercept. In a second order root, which happens when, say, for example, a certain factor in the polynomial is brought to the power of 2, that's where the word second order comes from. The shape of the graph at the x-intercept, which will be at 2 in this case, will be that of a turning point. And a third order root, which comes from the presence of a factor to the power brought to the power of 3 in the equation. And I'm taking x minus 2 as an example. Obviously, it can be anything else, any number. So here is x equals 2. The shape of the graph will be in that of a inflected point, we call this, or an S shape. Now, in the next example, what we're going to do is find the equation of a polynomial function with a given degree and the given zeros. So first, I like to read the problem, just in general, to get an idea what's going on. So find the equation of a polynomial function which has a degree 3. It has zeros at 3, and that's a double root or a double zero, and at negative 1. And this will pass through the point with coordinates negative 3, negative 144. So the first thing I want to focus on is the degree of the polynomial function, because that tells me that this function must be in the form y equals a, and I will have to list 3 factors in here because it's a third degree polynomial function. Now, the next thing you want to do is inspect the roots. So you're given the roots or the zeros at x equals 3. So if the root is at x equals 3, it means that x minus 3 must have been made 0 to obtain this root. So you kind of think backwards. So which means again that x minus 3 must have been a factor of this polynomial function. So I now know one of the factors. That would be x minus 3. And the next information that gets my attention here is the fact that this is a double root. A double root means that x minus 3 will repeat twice in the equation as a factor. And the last root in here is minus 1. So I first like to write the root or the statement about the root x equals negative 1. That tells me that this root has come from making x plus 1 equal to 0. So you simply take negative 1 to the other side. So we're thinking backwards, which tells me that x plus 1 is a factor of this polynomial function. So I will write x plus 1, and it doesn't give me information about it being a double or a triple root, first, second, or third order. So when information is not given, it means it's a first order root. So remember that we are asked to find the equation of this polynomial function, which means that we will have to identify the coefficient a as well. And for this, we will be using the coordinates of the given point with x equals negative 3 and y equals negative 144, which means that if I substituted the x and the y of this point into the equation that I have found so far, then that means that that will satisfy the equation. So instead of y, I will write negative 144 equals the unknown a, and instead of x, I will be writing negative 3. So I'm going to write the factors in here as they appear. So, and then negative 3 will go in place of x. Now, as you can see here, the only missing number here would be a, right? The coefficient that we're looking for. So that means that we're getting close to solving it. So we have negative 144 equals, I will leave a here, and I will simplify inside the brackets, obviously, just like bad math suggests. So that's negative 6, negative 6, negative 2. So that would be 36 times 2, that's 72 negative, equals negative 144. Divide both sides by negative 72. And we've just discovered that a equals positive 2. So now we can say with more confidence that the equation of this polynomial function, and I'm going to name it fancy, f of x, and that would be 2. Instead of writing x minus 3 times x minus 3, I'll write x minus 3 squared, and then x plus 1. And that's the answer. So this is the end of lesson U2A2, which is named after the bright space, actually, order we are teaching. So families of polynomial functions. And I would like to thank you again for choosing to learn from me. And let me know if you have any questions, comment in the comment section, and I will try to answer them. Or if you have any other topics that you would like me to discuss in the future. Thanks, and make your day beautiful. Bye for now.